Hello and welcome to our second lecture. Today we're going to finish chapter 1, finish the introduction by talking about classification of differential equations, and then we'll start talking about first order differential equations. Sometimes when we have a differential equation, the derivatives in the equation are only ordinary derivatives. If we have a differential equation which has only ordinary derivatives, then it's called an ordinary differential equation. In this course, on these slides, I'm going to be abbreviating ordinary differential equation as ODE. For example, two main equations that we looked at yesterday were the falling object equation and the mice and owls equations. These are ordinary differential equations because the derivatives in the equations are ordinary derivatives. If the derivatives in a derivatives in a differential equation are partial derivatives, or a mixture of ordinary derivatives and partial derivatives, then it is called a partial differential equation. For example, these two equations, the first one, which is called the heat equation, that describes how heat moves in a metal bar, and the second equation, which is called the wave equation, which describes how, for example, waves move on a guitar string. These are partial differential equations, or PDEs. This course is mostly about ODEs. If there's a single function to be found, then one differential equation is going to be enough. However, sometimes there will be two or more unknown functions, and then we would need a system of differential equations. For example, there's two equations written here. dx dt is ax minus alpha xy, and dy dt is equal to minus cy plus gamma xy, where a, alpha, c, and gamma are constants. There's two variables here, two unknown functions, x and y. These are both functions of t, and both of these functions appear in both equations. That means we can't find one function first and then use that to find the second function. Instead, we would need to find the two functions together. This system is called the predator-prey equations. This is beyond the scope of this course because these are nonlinear equations. When we get to the final chapter of this course, when we start studying systems of equations, we will only be looking at systems of linear equations. The order of a differential equation is the order of the highest derivative. For example, the falling object equation and the mice and owls equation both had a first order derivative in them, so they are first order ODEs. This equation, d squared y dt squared plus dy dt plus y. How many derivatives do we have? There's 0 derivatives here, 1 derivative just here, and the first term there's 2 derivatives. What is the highest number out of 0, 1, and 2? The highest number is 2. So this is a second order ordinary differential equation. And y triple prime, there's 3 derivatives, plus 2e to the power t, y double prime plus y prime is equal to t to the power 4. The highest derivative here is a third order derivative, so this is a third order ordinary differential equation. We can classify equations as linear or nonlinear. Let's look at the equation at the top first. We have some function of t, y, y prime, y double prime, y triple prime, etc. equal to 0. This equation is called linear if f is a linear function, and note here it's of y prime, y double prime, y triple prime, etc. We don't care about t. We don't care if it's a linear function of t or a nonlinear function of t. We're only looking at the y's. So typically, a linear equation looks like equation 1. That's some function of t, and then just one y term. We don't have y squared, we don't have cos y or e to the power y or anything else. It's just a derivative of y. And then plus, and then we come to the second part of the equation. Some function of t could be any function, doesn't matter. And then there's just one y. And so on. We always have a function of t, could be any function, but then there's just one y on its own. Nothing more complicated, just a y term, equal to some function of gt. For example, the falling object equation and the mice and owl equations are linear equations. Let me say this again. Let's suppose we cross out all of the function of t's. We don't care about t, we don't care if it's a linear function of t or a non-linear function. We really don't care. So just forget all of the functions of t. Let's suppose instead of gt we have 0, and instead of all of the at's we just have the number 1. Forget about all of these. And forget about the derivatives of y. We're not worried about the derivatives for now. So cross out the derivatives. What are we left with? We're left with y plus y plus y plus y plus y plus y equal to 0. This is what a linear equation looks like. If we have something more complicated after we've crossed out the functions of t and the derivatives, then our equation is not linear. Here's an example of a non-linear equation. Y triple prime plus e to the power t y double prime plus y prime is equal to t to the power 4. Let me use my trick. We don't care about the functions of t, so forget about these. We just cross these out. And we don't care about the derivatives, so cross out all the derivatives. Do we have y plus y plus y plus y is equal to 0? The answer is no. We have y plus y squared equal to 0. Y squared, we know the graph of x squared is not a straight line. This is a non-linear equation. For example, for each differential equation below, give the order of the equation and state whether it is linear or non-linear. Question for you. What is the order of this equation? There's 3 people saying it's a 5th order equation. Those people are correct. And there are 6 students, I think, who have fallen asleep. And is this a linear equation or a non-linear equation? That's more like it. 6 correct answers. This is a linear equation. Another one. D cubed y dx cubed plus cos of dy dx is equal to sine x. This is a third order equation. The biggest derivative is 3, but is this linear or non-linear? This is a non-linear equation. Why is it non-linear? Because we don't just have a derivative of y on its own. Instead, we have cos of dy dx. And we know that the graph of cos is not a straight line. The graph of cos goes up and down. So this is a non-linear equation. We can't have any functions of y or derivatives of y. We can only have complicated functions of the independent variable, which is in this equation is the x. What about this one? This equation is linear. We can cross out all of the functions of x. We don't care about sine x. We don't care about cos x. We're left with a derivative of y plus a derivative of y is equal to 0. So this is linear. Y double prime minus y squared is equal to x squared. Is this linear or non-linear? Remember that linear means that we can't have any functions of y. It needs to be y plus y plus y plus y is equal to 0 if we cross out all of the functions of x. This is a second order non-linear equation. It's non-linear because we have a y squared term. You can't have any y squareds in a linear equation. So this is non-linear. And the final one, e to the power x, 7 derivatives of y, minus x cubed, 99 derivatives of y plus 2x to the power x, y triple prime, minus x squared, e to the power sine x is equal to 2021. This time I'll tell you the answer. This is a 99th order equation, and this is a linear equation. Cross out all of the x's, we don't care about these. And we have y minus y plus y is equal to 0. So this is linear. That's the end of our introduction. Now we're going to start talking about first order differential equations. In this chapter, we're going to be considering equations of the form dy dt is equal to some function of t and y. And the first type of first order equations we're going to be considering is linear first order equations. So we're going to be looking at dy dt is equal to f of t and y, where our function f depends linearly on y. Remember, we don't care about t, we don't care what functions of t we have, but we want our function f to depend linearly on y. Last week we talked about equations of the form, not last week, last lesson, of the form dy dt is equal to minus ay plus b. This is a linear equation with constants a and b. Today we're going to generalize this a little bit. We're going to be talking about equations of the form dy dt plus some function p of ty is equal to some function g of t. We know how to solve equation 3. We did this yesterday, but let me very quickly recap it. What we want to do is we want to separate the variables. We want to move all of the y terms to the left and all of the t terms to the right. If we can do this, if we can separate the variables, then we're allowed to integrate both sides. After we've integrated, it's just a matter of rearranging to get y equal to something. For example, if we started with dy dt is equal dy dt plus 2y is equal to 3, we know how to find that the solution is y is equal to 3 over 2 plus a constant c e to the power minus 2t. Unfortunately, we can't use the same method to solve a more general first order equation. We're not going to be able to separate the variables. It's not going to be possible to move all of the y terms to the left and all the t terms to the right. So we're going to need a new method. And the method we're going to use is a method that comes from Leibniz. And the idea is this. Step 1, we're going to want to find a special function, mu t, which is called an integrating factor. We're going to multiply our differential equation by mu t, and then we're going to integrate. For example, use an integrating factor to solve dy dt plus 2y is equal to 3. I've just told you the answer to this equation. Using the method from yesterday, we know how to solve this. But now I want to use the new method. And you'll see that if we use the new method, we get the same answer. First, I want to multiply by the integrating factor. But suppose we don't know what integrating factor to use here. So we'll just use an unknown function, mu of t. Multiply everything by mu of t. We get mu of t dy dt plus 2 mu ty is equal to 3 mu t. And then we want to integrate this, but how can we choose the function mu t so that the left-hand side of this equation is integrable, and not just integrable, but easily integrable? Notice that By the product rule, the derivative of mu multiplied by y is mu t dy dt plus d mu dt y. And that sort of looks like what we had. We had the same green term, mu dy dt, in both lines. In the first line, we have the orange term 2 mu, and in the second line, we have the orange term d mu dt. We want to choose mu so that these are the same. We want to choose mu of t such that d mu dt is equal to 2 mu. We know how to solve this. We can use the method from yesterday. We can separate the variables and then integrate, and then we end up with some constant c e to the power 2t. We don't need to find the general integrating factor. We don't need to find every single integrating factor. We just need to find one integrating factor which works. So that means we could choose any non-zero value of c that we wanted. I like simple numbers, I like simple functions, so I'm going to choose c is equal to 1. So we're going to be using the integrating factor e to the power 2t. So we take our differential equation and we multiply it by e to the power 2t. E to the power 2t dy dt plus 2e to the power 2ty is equal to 3e to the power 2t. Okay? Because we chose our integrating factor very carefully, we can use the product rule on the left side, because the left side is just the same as the derivative of e to the power 2ty. Now this is looking easier. This is now an equation which we can easily integrate. The integral of the derivative of e to the power 2ty, of course, is just e to the power 2ty. And then on the right side, we integrate 3e to the power 2t to get 3 over 2 e to the 2t plus a constant. And then we're almost finished. All we need to do is divide by e to the power 2t to get the solution. And of course, this is exactly the same solution that we could get using the method from yesterday. So let me remark. For the differential equation dy dt plus 2y equal to 3, we use the integrating factor e to the power 2t. What about dy dt plus ay plus b? What integrating factor are we going to use? We could repeat the whole method that we used in the previous example. You can do this if you like. And we find that the integrating factor that we want is e to the power 8. Let's move on. Now let's make this a little bit more difficult. Now let's suppose that instead of just a number here, we have a function, gt. Solve dy dt plus ay is equal to g of t. The integrating factor doesn't depend on gt. The integrating factor only depends on the coefficient of y, which in this equation is a. So again, we're going to be wanting to use the integrating factor e to the power 80. We take our differential equations and we multiply it by e to the 80. Then we use the product rule on the left side. And look how easy it gets now. Instead of the complicated equation that we started with, we just have the derivative of e to the 80y, that's easy to integrate, we'll just remove the derivative, is equal to e to the power 80 gt. We can integrate both sides, and then we can divide by e to the power 80. Now, just to avoid confusion with the variables, I've changed to using the variable s inside the integral. Calculate the integral, and then I'm going to replace it with t. For example, this is an initial value problem. We have a differential equation and an initial condition. Solve dy dt plus half y equal to 2 plus t with the initial condition y of 0 is equal to 2. First, we're going to solve the differential equation, and then we're going to choose the value of the constant which satisfies the initial condition. So here we are. The differential equation had a half y in, so the integrating factor that we're going to use is e to the power a half t, or e to the power t over 2. We multiply our equation by this integrating factor, we use the product rule, and then we integrate. And I'm going to skip past the details. I'm going to leave this for you to check. I've had to use integration by parts here, with u equal to t and v equal to 2 e to the power t over 2. I leave this for you to check when you reread the lecture notes or when you rewatch this video. I'm saying that after we integrate, we get e to the power t over 2y is equal to 2t e to the power t over 2 plus c. Divide by e to the power t over 2, and we get the solution to the differential equation. To finish this problem, we need to choose the correct constant c. I want y of 0 to be equal to 2, but if we put 0 into our solution, we just get 0 plus c. So clearly, c must be equal to 2. So the solution to this initial value problem must be y is equal to 2t plus 2e to the power minus t over 2. Another one. Solve dy dt minus 2y is equal to 4 minus t. This one I'm not going to solve. Really, I'm leaving this as an exercise for you to do. What integrating factor do we want to use? We look at the number minus 2 here, and we see that we're going to want to use e to the power minus 2t. I'm going to leave it for you to check that if we use the method I've just shown you, we get the answer y is minus 7 over 4 plus t over 2 plus a constant c e to the power 2t. Instead of spending time there, I'm going to move straight on. Now let's make this a little bit more difficult. Now let's suppose that instead of a number here, we have a function t of t. What integrating factor are we going to use? I'll just give you a warning, a mistake a lot of students make. The integrating factor is not e to the power pt. Don't fall into a trap that a lot of students make. Don't fall into the trap of making the same mistake that a lot of students make. So let's start the way we did before. We'll take our differential equation and we'll multiply it by an unknown function, mu of t. On the left, we have mu dy dt, which I've written in green, plus pt mu, which I've written in orange. Y is equal to mu dt. As before, the left side looks a bit like the derivative of mu y. The green terms are the same. We want the orange terms to be the same. We want to have d mu dt is equal to pt mu, because we want to be able to use the product rule and then integrate. We know how to solve this. We can solve this by separating the variables. We can move all of the mu terms onto the left to get d mu divided by mu, and we can move all of the t terms to the right to get pt dt. Because we've separated the variables, all of the mu terms on the left, all of t terms on the right, we are allowed to integrate this equation. And after we've integrated and rearranged, we end up with a constant c multiplied by the exponential function of the integral of pt. As before, we can choose any non-zero constant that we want, so we can choose 1 if we want. And then we are left with the integrating factor e to the power integral of pt. It's not e to the power pt, it's e to the power integral of pt. Then, if we choose the correct integrating factor, our differential equation just becomes derivative of mu y is equal to mu g. Integrate both sides and rearrange, and we have a general solution. Let's do some examples. Solve ty prime plus 2y is equal to 4t squared with the initial condition y of 1 is equal to 2. The first thing to do is to write our general equation in the standard form. I want to have a 1 in front of dy dt, so I'm moving everything else in front of the y. In this case, I'm going to divide by t to get dy dt plus 2 over ty is equal to 4t. Then this is of the standard form, where the function p is 2 over t and the function g is 4t. We need the integrating factor. And the integrating factor is the exponential of the integral of pt. That's the exponential function of the integral of 2 over t dt, or e to the power 2 ln t, absolute value of t. Rearrange this, we get t squared. For this differential equation, we want t squared. So we multiply the differential equation by t squared. And in case there's any confusion, we're not multiplying the equation that we started with by t squared. We're multiplying the equation which is in the standard form by t squared. I'm going to take this equation and I'm going to multiply everything by t squared. Like this. So it's going to be t squared y dy dt plus 2t equal to 4t cubed. The left side is just the derivative of t squared y. So then we can integrate. T squared y is equal to t to the power 4 plus a constant. Divided by t squared, we get the solution to the differential equation. Y is equal to t squared plus c over t squared. All that's left is to choose the correct constant c. We want to satisfy y of 1 is equal to 2. To make this true, we need to choose c equal to 1. So the solution is y is equal to t squared plus 1 over t squared. And this is only true if t is a positive number. Because, of course, 1 divided by t squared goes wrong if we're dividing by 0. This red curve is our solution. Remember, the initial condition was y of 1 is equal to 2. So we must be passing through the point where x is 1 and y is 2. All of these blue curves are also solutions to the differential equation, but only the red curve satisfies the initial condition. So only the red curve is the solution to the initial value problem. I want to make some notes. Note that our solution is a differential function which is defined for positive x, defined for x between 0 and infinity, because it goes up to infinity as 0 decreases to 0. The solution becomes unbounded and asymptotic to the y-axis as t decreases to 0. This notation, if you haven't seen it before, is the same as t tends to 0 from the right. Makes more sense to me to write this downwards arrow. T is tending to 0 and t is decreasing. Why is this true? This is because our function pt, which is equal to 2 over t, has a discontinuity at t equal to 0. There's another function, t squared plus 1 over t squared for negative t. This is not part of the solution to the initial value problem. The solution to the initial value problem only exists between 0 and infinity. Anytime we have singularity, anytime the function goes to infinity, that's the end of the function. The solution doesn't magically join up with another piece. I also want to note that the solutions are behaving differently. We go back to this graph. Note that these solutions up here are going up to infinity as t decreases to 0, or t tends to 0 from the right. But these functions are going down to minus infinity. Somewhere in the middle, there's a point where this behavior changes. And in this case, the point where it changes, the initial value, is y of 1 equal to 0. A point where something changes is called a critical point, or in this, for a differential equation, this is a critical initial value. Our next topic for today is the topic of separable equations. Let's go back to the general first order equation. dy dx is f of x and y. In the previous section, we've looked at a special case called linear equations. Now we're going to be studying another special case. The general equation, dy dx is equal to f of x and y, can always be written in the form some function m plus some function n, dy dx is equal to 0. One way to do this would be to use m is equal to minus f and n equal to 1, but there's many other ways. If we can do this in such a way that m is a function only of x and n is a function only of y, then our equation becomes m of x plus n of y dy dx is equal to 0. This is a separable equation. The first order equation is called separable if we can rearrange it and write it of the form mx plus ny dy dx is equal to 0. If we can do this, then we can rearrange further to move all of the x terms to the left of the equal sign and all of the n terms to the right of the equal sign. In other words, it's possible to separate the variables. This is why it's called a separable equation. For example, consider dy dx is equal to x squared over 1 minus y squared. Part 1, show that this differential equation is separable, and part 2, solve this differential equation. We can rearrange this equation. I'll leave it for you to check. we can rearrange this to the form minus x squared plus 1 minus y squared dy dx is equal to 0. The green function is a function only of x. The orange function is a function only of y. So we have a separable equation. And now we want to solve this. Now, note that the derivative of minus 1/3 x cubed is minus x squared, and the derivative of y minus 1/3 y cubed is 1 minus y squared. So our differential equation is the same as the derivative of minus 1/3 x cubed plus the derivative of y minus 1/3 y squared, so y cubed, dy dx is equal to 0. But if you recall your chain rule from first year calculus, from first year multivariable calculus, remember that ddx of y minus 1/3 y cubed is the same as ddy of this function, dy dx. So really our differential equation can be written as the derivative with respect to x of this function minus 1/3 x cubed plus 1 minus 1/3 y cubed is equal to 0. And of course we can then integrate that to get this function is equal to a constant. Or rearrange slightly, x cubed minus 3y squared plus y cubed, so minus 3y plus y cubed is equal to a constant. Okay. And this is a different constant. I'm just not bothering to give the details that one is 3 multiplied by the other one or minus 3 multiplied by. It's just some constant. This same method can be used to solve any separable equation. If we start with mx plus ny y prime is equal to 0, suppose that we have two functions, h1 and h2, which are antiderivatives of m and n. Then we can write our differential equation as dh1 dx plus dh2 dy dx equal to 0. And by the chain rule, this is the same as dh1 dx plus dh2 dx is equal to 0. And then, of course, we can integrate to get the answer. h1 plus h2 is equal to a constant. So to recap, to solve our equation, we need to integrate m with respect to x. We need to find the antiderivative, so we're integrating. And we need to integrate n with respect to y. This is basically what we did yesterday. Yesterday, we solved it like this. We separated the variables so that all of the x terms are on the left, all the y terms on the right, and then we integrated. So we integrated m with respect to x, and we integrated n with respect to y. Basically, it's the same. This is why the method, which I said pure mathematicians don't like, this is why this method works. Now that I've explained why the method from yesterday and, in inverted commas, the proper method or the correct method are basically the same, we can use whichever one we want to use. Solve dy dx is equal to 3x squared plus 4x plus 2 divided by 2 y minus 1 with the initial condition y of 0 is equal to minus 1. I'm just going to separate the variables. Move all of the y terms to the left and all of the x terms to the right. And then I'm going to integrate. I get y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus c. To use the initial condition, to find the constant c, we use the initial condition, and I'll leave it for you to check that we must have that the constant c is equal to 3. So the solution to the initial value problem can be written like this. If we have a solution like this, where it's not just y equal to a function of x, but it's x and y's mixed together, a function of x is a function of y's, etc. This is called an implicit solution. Sometimes this is the best that we can do. Sometimes that's as far as we go, and then we just stop the answer. But in this example, we can go further. In this example, it's possible to solve this for y, because I can write it like this and see that this is a quadratic equation for y. Using our formula to solve a quadratic equation, y must be 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. The question I get asked a lot is there a mistake here? Should this really be 4? And the answer is, this is correct. This is not a mistake. This should be a 4 just here. I'll leave this for you to check why we get a 4 just here. Now, wait a minute. There's two solutions here, right? We have a solution with plus, and we have a solution with minus. Which one is correct? Which one gives us the initial condition y of 0 is equal to minus 1? If we replace every x by 0 and we replace the y by minus 1, we end up with minus 1 is equal to 1 plus or minus 2. To make this true, do we want 1 plus 2 or do we want 1 minus 2? And the answer is we want 1 minus 2. The solution to the initial value problem is the solution with a minus. Y is equal to 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. I can show you the graph on the next slide. If we have a solution which looks like y is equal to a function of x, this is called an explicit solution. If possible, we want an explicit solution. Sometimes the best that we can do is to give an implicit solution. Here's a graph of the solution. All of the blue lines are solutions to the differential equation, but only the red curve is the solution to the initial value problem. The top half, the one I'm pointing to with my mouse at the moment, is the solution with plus. This red part is the solution with minus. You can see that the solution is only defined from minus 2 to infinity. The solution is a differential function. with domain, the open interval from -2 to infinity. Another example, solve dy dx is equal to y cos x divided by 1 plus 2y squared with the initial condition y of 0 is equal to 1. I'll show you the whole calculation. This is not a perfect answer. If you wrote your exam question like this without all the details, you wouldn't get full marks, but for this example, I think this is enough. Separate the variables and then integrate. We get ln absolute value of y plus y squared, and on the right side we get sine x plus a constant. We use the initial condition to see that the constant must be 1, and then we finish with an implicit solution. I'll leave this for you to check. I'll leave this for you to fill in the details. This is not a perfect solution. This is not a full solution. Do better than this in your exam answers. This equation cannot be easily solved for y, so we're going to leave it as an implicit solution. But what can we say about this solution? We can say that if y is equal to 0, then the left side is minus infinity, but the right side is between 0 and 2. This means that y equal to 0 is not possible. So the solution must be always positive or always negative. But we know that the initial condition is y of 0 is equal to 1. So positive at least one point, so it must be positive everywhere. We could also say that the solution exists for all x between minus infinity and infinity, but I leave this for you to think about. The final topic for today is the differences between linear and non-linear equations. Today I'm going to be talking for more than an hour. Some lessons will be more than an hour, some lectures will be less than an hour. I start with a theorem for linear equations. Suppose we have two functions p and g which are continuous on some open interval. And suppose that the initial time, t0, is in this open interval, and y0 can just be any number. The theorem says then there exists a unique solution to this initial value problem on this open interval. It says two things. It says there exists a solution, it says there's always a solution, and it says that the solution is unique. There's only one solution. The theorem says that as long as our functions p and g are continuous, then the solution keeps existing. Or to say this another way, the solution can only stop existing at a point where either p or g has a discontinuity. Now let's go to a theorem for non-linear equations. Suppose now that f and df dy are continuous on a rectangle, t between alpha and beta, and y between gamma and delta. And let's suppose that the initial points t0 and y0 are also in these intervals. Here's a picture at the top. Let's suppose we have a blue rectangle for t between alpha and beta, and y between gamma and delta. And let's suppose that our initial point, t0, y0, is somewhere in this rectangle. We need to have f and df dy continuous on this blue rectangle. Then the theorem says that in some small interval around the initial point, there exists a unique solution to this initial value problem with a non-linear equation. Now, the theorem says that a little bit of solution exists. It doesn't tell us how much solution exists. It only says we have this little bit. We might have that the solution exists on the whole rectangle. We don't know. We might have that the solution exists for more than the blue rectangle. We don't know. All we know from the theorem is there's a very small bit of solution which exists. But it does tell us that two solutions to y prime equal to f of ty cannot intersect. To understand why this is true, suppose that in fact the opposite happened. Suppose that two solutions did intersect at a point. Suppose we have a solution which looks like this, and we have another solution which looks like this. And suppose that they are intersecting at the point t0, y0. But if this was true, then there would be two solutions to this initial value problem. And the theorem says this is not possible. The theorem says there exists a unique solution. So the key idea to remember from this section, which we'll be using next week, is solutions to first order equations do not intersect. And of course, this is with the proviso that we are assuming that f and the f dy are continuous on this open rectangle. And that's the end of today's lecture. Next time, that's next Wednesday, we will be continuing talking about first order equations. If you want to read ahead, we're going to be talking about sections 2.4, 2.5, and 2.6. That will be the end of chapter 2. Are there any questions? So for the next 45, 50 minutes, I'm available if you would like to ask questions. I understand that since you've just listened to me talk for 60 minutes, your mind might be a little bit asleep at the moment. So you might not. So sometimes what happens is students don't think of their questions straight away, but they think of something later. If that's the case for you, then please feel free to ask your questions on the discussion forum, and I'll try to answer them within a day.